Okay, so this is the last lecture of the course. Basically, I'm sorry I had to miss the last one, the previous one, day before, because I wasn't well. But anyway, it's just as well because I realized that I don't have anything to say about inflation because it can't be really discussed in one lecture. It would just be meaningless. So instead of that, I'm going to give you just in 10 minutes a little summary of something about the energy momentum tensor which I wanted to tell you in a previous lecture. That will complete our discussion for this course about cosmology. And then in the rest of today's lecture I will talk about orthonormal frames as promised. Okay. So what I want to say about the energy momentum tensor, first of all, is that I moved up a sign among many in this course when I introduced this concept. So let me review that again and correct the sign and then talk about the energy momentum tensor for scalar fields. As a technical concept, it's very useful in the discussion of anything to do with the early universe. And so you can use this and read whatever interests you from books. So the basic idea here is that we take an action, a field theory action, which is 1 over 16 pi g integral root minus del g r or x. This I think already differs by a minus sign from what I had before. This is the correct sign, I believe. My signs I think are all compatible with Sean Carroll's book. Okay. Now to this we add a Klein-Gordon or scalar field action, which I'll just call S matter. More generally, matter can include things like more generally it can include radiation as well and other stuff. But usually we model the matter by a scalar field, and so S matter. Okay, so before that, let me just look at the equations of motion. So what will S matter depend on? Some scalar field as well as the metric. You need to couple everything to the metric to have general coordinate invariant actions. Good. Now what will be the equation of motion of this total action? It will be 1 over 16 pi g. Okay, so the equation of motion is delta of S total by delta G upper mu nu equals 0, or we could take G lower mu nu, but term by term there may be some signs, so you have to decide one of them, and we just decide to take G upper mu nu. Now it's easy to remember what you get when you differentiate this, because remember that this thing is secretly G mu nu R mu nu. That's what R is. So if I differentiate with respect to this, I'm left with R mu nu, and there are no possible signs or factors in that term. Another term will come by differentiating this. That's a little more confusing, but we can see that because of this, this is 1 over 16 pi g, then root minus g, and then one term R mu nu. If one term is R mu nu, the other term has to be minus half G mu nu R. There is no choice, because this is the combination that must occur in isometric motions. Okay. Actually, the reason for the minus is because this is root of det of G, and we are differentiating in G inverse, so it's a little bit complicated. The reason for the half is because of the square root, whatever, but basically this is the first term. Now the second term, of course, is nothing but plus delta S matter by delta G mu nu. So this whole thing has to be 0. That's the equation of motion of G. But now we define T mu nu, the energy momentum tensor, to be minus 2 over root of minus G delta S matter by delta G mu nu. Some people define T upper mu nu in terms of this differentiated in G lower mu nu, that has a sign difference with respect to this, unfortunately. So it does matter whether you differentiate with respect to G upper or with respect to G lower, and then you get raised indices and then you lower the indices. Those two operations actually don't come. It's basically the fact is that when I have a matrix and its inverse, varying the matrix and varying the inverse are somehow opposite operations. So depending which one I choose to do, I get different answers. Okay, good. So with these conventions, I can take this to the other side and write it as minus a half. Sorry, as okay. So this gives me that R mu nu minus half G mu nu R is 8 pi G. This is correct. Of course, we have always used this, but I just wanted to make these definitions clear. Now, let me choose for S matter the Lagrangian for a Klein-Gordon or scalar field. The Lagrangian always has the form of T minus V. T is the kinetic energy, V is the potential energy. So V always comes with a minus. In the convention, sorry, G, thank you. In the conventions we use this term. If you look at the time component, G00 in flat space will be minus 1, and therefore there will be a plus, and therefore it will be phi dot squared. And phi dot squared is the kinetic part. The remaining part where this mu nu takes values over I and j, that is the potential part, that should come with the minus. That's how you remember the sign of this. Okay? So good. So with this definition, T mu nu is plus del mu phi. That comes by, there's always a half here for a real field. The half stays, it goes because of this 2 multiplication, minus 2, minus removes that minus sign, 2 removes the half, 1 by this removes the root minus g, and so I have this as the first term, and then the rest of it is minus a half g mu nu G alpha beta del alpha phi del beta phi plus V phi. So this is T for a scalar field. This much should not surprise you. Now the interesting thing is that it's of the form something times u mu u nu plus something else times g mu nu. If we take u mu to be proportional to delta mu phi, del mu of phi. So where have we seen that? The energy momentum tensor of a perfect fluid was taken to be proportional to u mu, where u was the velocity for vector, and a term proportional to g mu nu. And we see that if we think of the gradient of this scalar field as the velocity for vector, then this expansion has the same form. One piece is proportional to g and one piece is proportional to u mu. Now of course, u is a normalized velocity for vector. It should have norm u mu times u mu contracted with the metric should be minus 1. That's not true of this thing. So in fact, after normalizing, u mu comes out to be del mu phi upon square root of minus g alpha beta del alpha phi. With this normalization, if I take u mu and contract it with another u mu, I'll get minus 1. Only after I have normalized it in this way, then I can ask what's the coefficient of u mu in this expansion. And what I find is that T mu nu is writable as minus g alpha beta d alpha phi d beta phi a scalar quantity times u mu plus, rather again minus half. Now I'm just copying a term from here times dV. So now I have the perfect fluid form. And the nice thing is, because of this, I can read off what would be the pressure and the density of the perfect fluid made up of this. Of course, in some sense, yes.
After should become phi also.
Where? Here?
Either there or here.
Yeah, you're quite right. I think it's actually here. Either there or here. So which one is it? Sorry, I think this is, it's here. Now I'm not so sure. 1 minute. No, it can't. No, this is the. You see, the sum of these two terms is the same as the sum of these two terms up to a time. Because for this contribution we are differentiating this. So whatever factor we get, actually there was a half and a minus, but both were killed by the definition of union. But whatever is inside is just this thing carried over. So the relative factor is fixed by that. So this is fine. So it's perfect fluid form. But of course we know that in a perfect fluid, the coefficient, so this should be the same as rho plus P. So P G mu not equals P G mu plus rho plus P u mu. This we already argued. And therefore from this we read off that P is equal to minus a half G alpha beta del alpha phi minus G of phi, and rho is whatever it is such that when I add it to P, then I get this. So it is minus a half G alpha beta del alpha phi del beta phi plus G of phi. Okay. Now these are just names. I'm just identifying that the thing which we called P earlier and rho earlier with this energy momentum tensor is really this thing and this thing. In other words, if I now try to do some cosmology and so on, then I should simply, wherever I had P and rho, I should now have this thing and this thing. Before that, I have to just make sure that I've implemented my assumption of isotropy and being in co-moving coordinates, and it's pretty clear that I'm not yet in those, I'm not in the rest frame of the fluid because I have u mu equals del mu phi upon square root of minus G alpha beta. So it's correctly normalized, but it's a 4 vector with all 4 components, non-zero. Rest frame of the fluid would mean that ui is 0 for I equals 1, 2, 3. So in fact u becomes 1, 0, 0, 0. That's the rest frame. So what does that tell me here? That tells me del I phi equals 0 for I for the space directions. That tells me that phi is a function of time only. There's no surprise. We have a scalar field which is a number, a value at every point of space-time. What we are saying is for things to be homogeneous, that number should be independent of space, but it can depend on time because the universe is evolving in time. It's just part of the assumption of homogeneous and isotropic universe applied now to the scalar field. But once we have this nice simplification, then first of all u indeed becomes of the form 1 0 0 0 because u mu is phi dot and this is square root of minus phi dot squared. Square root of phi dot squared. So it's really 1. Because in co-moving coordinates g0 0 is minus 1. So that this whole term reduces to phi dot. This also reduces to phi dot. We get 1 because it has to be. Okay. From this it follows that the pressure is now. Okay. We also have to be in co-moving. So we choose the metric in co-moving coordinates, which is the usual choice that we've always made in such discussions. So G00 is minus 1 and G0I is 0. So with that, we can now write P and rho quite nicely. P is just plus 1/2 phi dot squared minus V and rho is half phi dot squared plus. So that's simple enough. Now you can see why I panicked about my definition of T mu nu earlier. What the definition I had given you earlier would have told me that P is minus of this whole thing and rho is minus of this whole thing. It probably wouldn't have affected some of the Friedman equation, but some of it would have affected. And moreover, rho would have been always negative while here. The sign of it for in the absence of a potential, both pressure and density should naturally be positive. Okay.
Last time it was 2 by 2 minus the variation of S prime order.
Exactly. Plus 2. Now it's minus. That's yeah. So if you use my last time definition, you would have found a minus in this, which I think is not very pleasant. Okay. Now notice something nice. You see, earlier P and rho were just some names we had given to the energy momentum tensor components. And then we had to say, well, there's an equation of state and P is proportional to rho, but we couldn't justify that on any fundamental terms. It had to be justified from experiment or from some choice of effective description. But now, first of all, notice that P is not proportional to rho. They are simply two independent functions. However, they are completely given in terms of the potential of the underlying scalar field theory, which is some fundamental quantity. So once that's given, then P and rho are given. They are both time dependent because phi is time dependent as expected, but P upon rho is not constant. So in some ways you should consider this a better equation. It's a better substitute for the equation of state. Instead of postulating something with a number W, you have actually got P and rho in terms of some fundamental object, and this is what you should use. So now you can cycle everything we did before. In particular, you can cycle the Friedman equations again. But we don't need to go through the derivation, because the equation is nothing but equating R mu nu minus half G mu nu R to the right side depending on P and rho. So we can take the equations and substitute in them that P is this and rho is this, and we are done. And that's all I wanted to show you. So let's just look at one of the equations. We got this equation by using both the Friedman equations. It was particularly useful because it gave me a direct relation to the Hubble parameter h of t. So now I just need to plug into these guys. So rho dot is phi dot phi double dot plus v prime phi dot. Downstairs, P plus rho is just phi dot square. Okay. Now I can actually cancel phi dot from here, here, and here, and we get phi double dot plus 3h phi dot plus v prime equals 0. So now see what a nice thing has happened. From the Friedman equation, we found an equation for the scalar field second derivative. The scalar field itself, being a function only of time, for all purposes behaves like the coordinate of a particle, non-relativistic particle, moving in a potential V. Okay? For such a situation, the equation of motion for that non-relativistic particle would have been x double dot plus v prime equals 0. Okay, and that's what we get, except that we see this friction term, and the friction term depends on the Hubble constant. In fact, the coefficient of friction is 3 times the Hubble constant. Okay, but it's not a constant, so it's a time-dependent friction term, so it's not that simple. But in any case, h is nothing but a dot upon a, and a is another function of time. So it's really like a coupled system of phi and a. There's a scalar field evolving, and the universe, its scale factor a evolving together in a coupled way. This is one of the equations, and the other Friedman equation can be written down immediately. Remember, one of them depended on the curvature k. So whenever we write down two independent equations, one of them must depend on k, otherwise we'll never find k from the Friedman equation, then we would have lost some information. So the second Friedman, other Friedman equation, actually it might be the first one, when translated into this language, just says that a dot squared is equal to 8 pi g by 3 a squared into phi dot squared by 2 plus v for phi times k. So there you have it, a pair of equations for the dynamical evolution of phi of t and a of t. And all the information from Einstein equations is contained in these two equations. Okay, so now the only thing that's in your hand is, of course, to specify the potential V of phi and to specify the initial conditions, and then watch the system evolve. Okay, obviously, what you have to match on to experimentally is that A of t should be whatever we see it to be today. Okay, A of t is observed in the form of the Hubble parameter. That should be what we see today. Now, inflation is one. Yes.
That can be taken as an initial, say some kind of boundary condition of this.
Yeah, it is a kind of boundary condition. Thank you. Sorry, you're quite right. Well, actually, the question was what would happen to the field equation I get by varying phi, and here, why do I think it's included here? Because let's assume there was no metric. Let's assume we had a flat metric in the problem. Then Hubble parameter is 0. Phi, supposing we take it independent of space, then the field equation is nothing. The field equation is box phi is equal to field prime. Okay, but that's this equation if you remove h, right? So this must be also the field equation for phi. I think the way it happens is that the energy momentum tensor being conserved was we got this from conservation of energy momentum tensor. I think that was one way of getting it. So I think we've used all the equations. I'm not 100% sure, but I don't think there are any more equations. Well, there's the equation of, I don't think there are any more. I think this is it.
There is no friction term in the equation of motion.
There is, if you couple it to gravity and isocouple it to gravity, then there will be. In fact, thank you. I think one way I can write it is, supposing you are formally inclined and you think of the equation of motion for this action as an interesting question. So the equation of motion can only be d mu del mu phi equals minus v prime phi. What is this? This is, maybe it's better if I write it this way. So this is equal to del mu, ordinary del mu phi. So this modification to capital D mu comes about because we have coupled the metric to this. So of course, without any even looking at details, we can be sure that the metric will do the job of converting the ordinary Klein-Gordon to the generally covariant Klein-Gordon equation. So it just means you replace what small d by capital D here. This one is okay because it was acting on a scalar field. Next one acting on a vector field needs the affine connection term. So it's this plus gamma mu lambda del lambda phi equals minus v prime phi. Now, unless I think I've already bungled the sign, so probably let's assume this is plus. Now, if I take this to be only dependent on time and the metric to be in co-moving coordinates, then I can lower the del 0 at the cost of a minus, take it to the other side, and I've got phi double dot plus v prime. And now I'm prepared to bet anything you like that this term will turn into a dot upon a times phi dot with 3. So the frictional term comes from. Okay, good. So now in studies of the early universe, it depends on what kind of physics you want to reproduce. If for some reason you want to show or you want to create a universe which behaves in a certain way, for example, expands very rapidly. I don't have all the time to go into reasons why we think that happened. But suppose you wanted to expand very rapidly and then expand slowly after that, which is basically the idea of inflation. Then how would you arrange it? You would arrange it so that the evolution of this field phi in its potential V has some appropriate form such that it evolves at different rates at different periods, and its evolution, because of the nature of coupling between these two equations, drives the evolution of the universe. So you can drive the behavior of A of t to be what you want by choosing the potential so that it drives the behavior of phi, but of course in a self-consistent way. The basic tool in your hand now is the choice of potential. Nothing stops you assuming that instead of one scalar field there are 20 scalar fields, then you have what is called multi-field inflation, then you can tune a huge potential of any variables and write lots of papers. So this is sort of how it can be. Okay. Good. So that is just to really tidy up the last lecture, and that's all I want to say about cosmology, because I think it's enough. I think we have actually, I'm pretty convinced now that we have done all the GR techniques that are needed for cosmology. Anything that's not been done here and is needed for cosmology would not be a technique, but it would be something directly related to observation and directly related to our beliefs about the early universe, how it evolved and so on, and that's something of a whole other course. Anyway, any discussion that you read will always present this frictional damped equation as a key equation, and from here you jump directly into discussions of inflation, quintessence, and whatever. Okay. Good. So now in the remaining time, I want to change topic altogether and talk about orthonormal frames. It's a very useful conceptual tool. Again, there's lots you can do with it. I'm not a complete expert, but I understand that even if you really want to calculate a lot of properties of black holes, of short-scale black holes and whatever, this might even provide a more useful formalism to do the calculations. So it can be even practically useful, but it's very conceptually useful. And let me just first give you a sort of pictorial idea of it, and then we'll do the equations, which are not very good. So first let's work with space, and let it be three-dimensional space, no space-time here. And let's assume we are in a space which is very curved and complicated. Okay. Now, the big problem with studying this is that there is general coordinate invariance built into our laws, and so we have to be prepared whenever we talk about any quantity at a point, a function or a vector or a tensor. We have to be prepared that it will change every time we change our coordinates. Now that's a nuisance, but we can convert it into an advantage by the following observation. Supposing at a given point, let me write the word here, at a given point, select 3 linearly independent vectors, 3 vectors. Okay, an obvious choice might be in some coordinates to say that they are the 3 vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1. Those are 3 linearly independent vectors and those are called basis vectors. Okay, so let's try to do something similar here. Select 3 linearly independent 3 vectors and let's label them EI alpha. I'll answer your question in a second. Or E vector alpha. I equals 1, 2, 3 labels components. That means the vector E alpha for a fixed alpha has components E alpha 1, E alpha 2, E alpha 3. But alpha equals 1, 2, 3 label 3 different vectors. Is this point clear what I mean by 3 independent 3 vectors? Yeah. So let's choose these to form a basis. If they are linearly independent, they form a basis, which means I can refer any calculation to this basis if I like. Okay. Yes. No. So in fact, they are going to be, what are they going to be? Good. So in fact, for that purpose, maybe I should abandon this notation. There are 3 linearly independent 3 vectors. They should be thought of as technically as living in the cotangent space of the manifold. Okay, but in the language that we've been using, they're just covariant vector fields. And I'll write down immediately what that means. So the fact that there are 3 vectors on the manifold means that I is an index which transforms under general coordinate transformations. But alpha is merely a label for 3 different vectors. So under GCT, so today I'll talk about general coordinate transformations a lot, so I'll use GCT. Xi goes to xi prime of x. In a few minutes we'll generalize this to space-time, but right now we'll just be in space because it's easier to talk about that. So E I alpha, E prime is nothing but del x j E j alpha of x, which simply tells me that the index I behaves like a covariant or lower vector index and the index alpha doesn't do anything. It simply doesn't play a role. Independently, the vector E1i transforms this way, the vector E2i also transforms this way, and the vector E3i, the third one, also transforms the same way. Where all vectors transform the same way, right? Okay. It's important to understand because it's the first time we are encountering an object with 2 labels, but really only one of them is a vector index, the other is just a label. We could as well have called it red, green and blue at this moment. Now, however, so we are introducing this. I haven't given you perhaps a complete motivation, but just to tell you very roughly, what I want to do eventually is to take all other vectors and tensors which transform under general coordinate transformations and measure them in some kind of frame determined by these vectors. So these vectors will play a central role in the discussion. We'll refer everything else to these and we'll find that then dealing with general coordinate transformations is simplified. We'll see that in fact you can avoid dealing with general coordinate transformations forever, but you have to pay a price. That's the philosophy. So let's now do it. Now one question that will arise, of course, is there are so many ways of choosing such vectors. So let's do one thing. Let's make them orthonormal. If we make them orthonormal, we'll think of the title, then we have ruled out many ways of choosing the vectors. For example, we no longer are allowed to change the angles between them, and we are no longer allowed to change their lengths. They are orthogonal to each other, and each of them is normalized to 1. So, orthonormal means what? Here, of course, we encounter the fact that we are on a manifold and not in R3. So, what I want to do is take EI alpha and EJ beta. Okay? So, where alpha and beta are labels which could be equal or different. If they are different, then, and I want to contract I with j, I want to dot the vectors. Dotting the vector means dotting the components of this with the components of that. But there's only one meaningful way to contract these, which is to introduce the metric here. Otherwise, what I do will be dependent on the coordinate basis, and that's just what I don't want. So, it makes perfect sense for this to be my orthonormality condition. It means the norm of a vector, when alpha is equal to beta, then this would be the norm of the vector, as measured in the presence of the metric, is 1. And of course, the dot product of two vectors, again dotted in the presence of the metric, is 0. So they are orthonormal. Okay. Now this cuts down a lot of freedom in specifying these orthonormal frames once we have got them to be orthonormal. Because as I said, we can't make any changes in them which spoil this property. But there's still one change we can make in them which preserves the property. What is that? We can still rotate them among themselves. But now be very clear what we are doing. Rotate means I've got 3 chosen orthonormal vectors. Okay, I can take the whole thing and move it around. That I can do. Okay. Now so that means I can send E alpha I to M alpha beta E beta I. Now for the first time I am carrying out an operation on this upper index, which is the label. Okay? Because it's the label which I am rotating. I am not doing anything to the components of the vectors as far as the space-time is concerned. I am just rotating the definition among the 3 vectors. So the new vectors will be linear combinations of the old ones.
Sir, I mean, in a general curve space, is it guaranteed that a rotation will take, this set will be closed under this kind of rotation?
Yeah, that's the same question as asking if I have a covariant vector field, 2 covariant vector fields, and if I add them, is the result a covariant vector field with this transformation law? Answer is yes. And that's the beautiful fact, and it's the same fact we are using today, that although the manifold is curved, these vectors don't live in the manifold, they live in what is called the tangent space, and that thing is flat. In fact, this is one thing that Nitin explained quite a lot in his lecture. The tangent space is a vector space. Because it's a vector space, you can add and subtract vectors just as much as you feel like. Okay? And the whole trick of orthonormal frames is to move away from considering the manifold and consider only the tangent space.
Tangent space is a vector space or a matrix space? On a manifold.
It's a vector space. A vector space is something where there's a vector called 0. For every vector, there's minus of that vector. Given 2 vectors, the sum is another vector. All those are its dimension is also equal to the dimension of the manifold. You're probably thinking there has to be some catch in this. It can't be that with a curved manifold I can just move into the tangent space and say now I'm in flat space forever. The catch is the following. I can do it here, you can do it there, but this tangent space and this tangent space aren't the same, where the whole tangent space itself moves because of the curvature of the manifold. Okay, so that's the catch. In fact, that catch tells me that I am free to rotate this thing, which is a function of x, by a matrix which is a function of x, times these which are functions of x. Because look at this condition. This whole condition is at a fixed point x. E of x, g of x equals constant. Okay. So if I introduce such a rotation matrix here, then this will be invariant if M satisfies what? MM transpose is 1. If MM transpose is 1, then EI is preserved. If and only if. This is the maximum amount of transformation I can make on these things which preserves the relation. But crucially, it allows me to make this transformation independently at every point of the space. I can choose this matrix independently, but of course at every point it has to satisfy this constraint. But it still has some parameters, those I can vary. Yes.
Sir, I am choosing here 3 linearly independent 3 vectors.
Yes.
That means E alpha I H, where alpha is the level of the 3 vectors,
Yes.
independent vectors.
Yes.
So I can say that in the tangent plane, I have the 3 alpha 1, 2, 3. They are in the tangent plane.
Their basis in the tangent space.
No, the vectors themselves, see, even if I had only alpha equals 1, I would have one vector in the, that would be in the, actually it's technically called the cotangent plane. If the index was up, it would be in the tangent plane. Tangent space.
That is in the tangent plane. But if I say I fix alpha equals to 1,
Yes.
then alpha 1, I equal to 1, 2, 3.
Yes, that's a vector, that's one whole vector.
They also will be in the tangent plane, tangent or cotangent plane.
No, the whole thing, so I fix alpha equals 1. Then E1, E2, E3 is a triplet which forms a 3 vector, that means 1 3 vector in the tangent space. So it's one element of the tangent space.
Then for
Now
alpha,
I do it same for alpha equals 2 and 3, so I get 3 elements of the tangent space. The reason I want 3 is to form a basis. 1 will not be enough to form a basis.
and the
But 3
basis is in the tangent.
in the tangent plane. Okay. Technically again in the cotangent plane because of the index being down. Okay, tangent plane if the index was up. I could have done this whole thing more or less equally well with the index up. Actually, many discussions start that way. In fact, the mathematicians prefer to do that because they prefer the tangent space rather than the cotangent. It doesn't matter for us. Okay. But what I'm saying is that this kind of rotation is something that we certainly know in ordinary R3. For example, if somebody gives you 1, 0, 0, 0, 1, 0 and 0, 0, 1, you are free to take some new vectors which might be 1, 1, 0 or 0, 1, 1 or whatever, right? These are some new set of vectors, but as you can see, they are nothing but linear combinations of these. Okay? And these will be as good a basis as these if the matrix transforming these to these is a matrix in O3, orthogonal matrix or rotation matrix. Because then whatever conditions this satisfies, that they are all normalized to unity and orthogonal to each other, will be true here. Of course not for what I've written probably, but whatever. So that was a bad choice, but something. There are things that we can do. So any orthogonal transform. Good. Okay.
Sir,
Yes.
I will ask one question. Suppose I have 3 linearly independent vectors 1, 0, 0, 0, 1, 0 in ordinary 3 space 0, 1, 0, 0, 0, 1. I can generate any other basis from them, but I will consider only those which are generated from those by rotation.
No, only those will be orthonormal, otherwise they won't. So all orthonormal bases are generated from one of them by orthogonal rotation. Actually, that's a beautiful fact that you can start with any one, and everything that's possible is related to that by orthogonal rotation.
If they has to be orthogonal.
Yeah, if they are orthonormal. And the proof is very simple. You don't need to go to equations. Imagine that you have some basis, okay, and you want to convert it into a standard one. Then just realize that both the bases look like rigid body, which is identical with different orientation. So there must be some rotation which has to come.
Euler angle will please.
Euler angles will tell you. Good. Okay. Now notice, now it becomes more interesting. So we've seen one thing. So we've got the following two properties. This property under general coordinate transformations, and also this property under a group which I will call local rotations, which is here O3. Notice that in this one the transformation is all at the same point, but of course in this one, even though it's the same point, the label of the point is changing because we are doing a general coordinate transformation. Here we are not doing anything to the coordinates. Very important to distinguish that. Here nothing is being done to the coordinates. Same coordinates before and after. We may still refer to the left side as E prime and write this equation. E prime is equal to that. But it's not E prime obtained by a general coordinate transformation from E, but by a local rotation from E. Okay, so this E prime has a different meaning from this E prime. If you want, this is the one which is primed but with respect to the upper index. This one is primed but with respect to the lower index. Okay. Now, viewed as a 3 by 3 matrix, of course, it's quite surprising that we should view it that way because it's really 3 vectors, but of course it has two indices alpha and I, so it's a 3 by 3 matrix, whether you like it or not. This equation gives us some information. It says that determinant of E squared times determinant of G inverse is 1. Right? Because this equation is E G inverse E equals 1 in matrix language. The same equation. Right? Now take determinant of everything, you get this. So you learn that E is square root of det of G. Det of E is square root of det of G, which means since G being a metric is non-singular, E is also non-singular as such a matrix, which means we are free to invert these E's as matrices. Notice that E is not even symmetric. It doesn't even mean anything to ask if it's symmetric because one index and the other index have completely different meanings, so you can't exchange the indices. There's always one of one type and one of a different type, but still it's non-singular. Okay. Now consider the following combination: EI alpha, EJ alpha, this time sum over alpha. And I could put the sum, but I'll ask you to use the summation convention for the index alpha. We just sum over alpha going from 1 to 3. Okay, there's some matrix. I'll call it pi ij. I don't know what it is. Okay. Notice that this is a different way of contracting two E's to get a matrix. Here we contracted the indices I and j, but here we've contracted the indices alpha and beta. So we've got some matrix. So let's try to find out what we can say about pi. So first suspicious fact is that the determinant of pi is square of determinant of E, which means it's equal to determinant of G. That's nice. But we can do more than that. Let's multiply this whole equation by E k beta G j k on both sides. So we have E I alpha, E j alpha, E k beta G j k is equal to pi I j G j k times E k beta. Now here I can take this stuff and use this equation. So what does it become? Delta alpha beta. So that when contracted with this converts this alpha to a beta. So we find that E I beta is equal to pi I j G j k E k beta. Now E is invertible as a matrix, so I can cancel off E from both sides and find that delta Ik is equal to pi ij k. What does that tell me about the relation between pi and g? Pi is inverse of g upper, which is the inverse of g. Therefore, pi is g. As you know, in matrices, when I have the inverse of a matrix, it's unique. So the inverse of the inverse has to be the original matrix, no choice. So what have we learned? We've got a very nice relation which is suitable to be written just below this one. This we already got from the beginning. This is the orthonormality. The new relation we've got is this one, which I'm going to write Ei alpha Ej beta delta alpha beta is equal to Gij. Now you have to keep these equations look so similar that it's easy to get confused. So you have to keep reminding yourself that they have different meanings. This is an equation normalizing a set of vectors. Okay, this is more like a completeness relation. This says take the vectors contracted with delta. That means take E1 times E1, the ij component, plus E2, E2, the ij component, plus E3, E3, the ij component. Whatever I get is the metric of the space. So you can think of this one as normalization, orthonormalization, and this one as completeness. Anyway, the point is that this one we proposed because it's part of the definition, but this one we just derived. We didn't propose this extra, it just follows. Okay. Now notice that this equation is also compatible with the fact that det of E is square root of det of G. In fact, this equation tells us that E is the square root of G. This equation, if you want to think of it that way, says that E transpose is G. If you think of it as an equation for matrices. So in that sense, E is like a square root of G, viewed as a matrix. So surprisingly, E is very interesting, viewed as a matrix, even though we were never supposed to view it as a matrix. We were only supposed to view it as three vectors. Good. Okay. Now I said that E is invertible, so it must have an inverse, which I've never written down. So now let's define the inverse. There's a question. Okay. Define E capital. Now its index I should be up, and for convenience I'll keep the index alpha down. Actually alpha really doesn't matter where it is. So now I'll keep it up, but we'll see that later. Down is a better place for it. So the idea is that we contract in this way. Probably I should think of these small e's as having I first and beta later, and these as having alpha first and I later. So now E times E. Actually, I don't like this. I think it's the other way. I should think of these e's as having their index alpha first and I later. So the inverse will be like this. Of course, you know that right inverse and left inverse are the same. That's another theorem about matrices. So this is the correct way to define capital. Alright. Now, once we've done this, it's very obvious to show the following identities. If I take Ei alpha and Ej beta, if I contract with Gij, this time with G, not the inverse of G which was appearing here, I expect to get what? Delta alpha beta. And if I contract instead the same pair with delta alpha beta, then I expect to get
G
upper I. All perfectly consistent and perfectly inverse to those relations. Okay? Great. Now I can immediately start and tell you what good these things are, because finally I have to tell you that. But at this moment I would like to switch to 3 plus 1D space-time. I emphasize that the use of these is pretty much equal in space or space-time. I mean, they work perfectly in both cases. But just so for you to get used to the notation and for me to point out one little difference. Now you see, in space, the group which allows us to rotate this set of 3 vectors is O3. But in space-time, the corresponding group is O3, 1, the Lorentz group. Okay. So we have to be a little careful. And so now in space-time, what I'll do is I'll write this as EA mu. A will be the space-time index taking values 0, 1, 2, 3 in place of alpha, and mu will be 0, 1, 2, 3 in place of I. Okay, so this is called the general the GCP index. But now when I write EA mu E B mu and contract with G mu nu, what should I expect to get? I should expect to get eta AB, because these AB are really like flat space-time indices, because the tangent space-time of curved space-time is flat space-time. Okay, so in some way you can think that this index behaves like special relativity and this index behaves like general relativity. Good. Now this is invariant. This relation is invariant if I send EA mu to lambda A B E B mu, where lambda eta lambda transpose eta as a matrix. This is called a Lorentz transformation. If this had to, if eta had been replaced by delta, which is the same as 1, then lambda transpose was 1 and we would have orthogonal rotations. But because eta is minus 1 and plus 1 plus 1 plus 1, whatever lambda comes out to be are Lorentz transformations. This is the definition of Lorentz transformations. But remember, this is the dangerous part. Everything depends on x. So lambda are called local Lorentz transformations. And now all the consequences come out nicely, but wherever we reduce our difficulty in terms of GCPs, we will be increasing our difficulty in terms of LLTs, local Lorentz transformations. But we must never forget that even if difficulty is somehow conserved, we are mapping the problem of one kind of group to another kind of group. The group of general coordinate transformations and the group of local Lorentz transformations are extremely different from each other. We'll see that more and more. So I have about 15 minutes during which I'll show you now what we can do with this. Okay. So here's what we can do. We can use this formalism in general relativity to convert any tensor under GCP to a scalar. Isn't that wonderful? You don't have to deal with GCP tensors. Here's an example. Take V upper mu. So it's a contravariant vector. You know how it transforms under general coordinate transformations. Multiplied by E A mu. I think I should should have stuck to E upper. See, this being up and down doesn't matter much, it only matters up to a minus sign. This index being up and down matters up to a factor of the metric. But this one is raised and lowered by eta. So all these relations are true regardless whether it's up or down. But eta upper AD is the same as eta lower AD. So it doesn't matter at all. But I think I'll prefer this. I'll prefer this because so in that case he has index A here and mu here. The result I'll call VA. The definition of V. Now notice something. We are in some coordinate basis. Then V mu, if we are in some choice of coordinates, V mu of x has some dependence on x. But E mu also has a dependence on x. So don't think that the new VA has the same functional dependence as this, because it could be much more complicated because of this guy's dependence on x. Right? However, it's an invertible transformation. I can go back anytime if I feel uneasy with this guy, I can go back to that one because V mu is equal to E mu A V A. Right, where capital A is the inverse. So it's certainly invertible. What are the benefits and disadvantages? In school they used to ask this question. Compare and contrast these two chemicals. Ferric oxide and ammonium nitrate. There's nothing to do with each other. Anyway, so let's compare and contrast V mu and VA. So V mu is a general coordinate vector and it knows nothing about local Lorentz transformations. VA is a general coordinate scalar, but it's a local Lorentz vector. Okay. What is going on? What's going on is, it's best to say in words. If I make a general coordinate transformation, this transforms, but this also transforms. The transformation cancels out because the mu indices are contracted. So this is invariant. So this is what I promised. Scalar under general coordinate. On the other hand, if I make an LLT, local Lorentz transformation, this doesn't care, but this transforms. Okay. Therefore, this also transforms. So vector under LLT. So we've given up something and we've got something else. Okay. So in fact, under GCT, let's be very explicit for once. Under GCT, V prime A of x prime is just V A of x. It's a scalar. It's a set of scalars. For each value A, it's another scalar. Okay. Why? Because for each value of A, I used one of the vectors in the orthonormal frames to dot with V mu and produce a scalar. If I dot a vector with a vector, then I produce a scalar. On the other hand, under LLP, V prime A of x, not of x prime, is lambda AB of x, VB of x. So this is the statement that effectively GCT gets replaced by LP. And you can see that if I had a tensor with many indices, I would just multiply by many e's. Each one would remove one of these indices and replace it with one of these indices. If it had indices down, I would multiply it with capital E's. Those would remove the lower GCT indices and replace them by lower LLP indices. Okay, so whatever the tensor, I can get rid of all its GCT indices and end up that I don't have to worry about GCTs ever again. Okay. So now let's start asking some uncomfortable questions. If VA is an LLP vector, is d mu VA is it what we expect? What we expect from its synthesis is that it should be an LLT vector and GCT vector. Remember that d mu means d by d x mu. X mu is a coordinate. So x mu cannot be converted into something which doesn't know about coordinate transformation. It is the coordinate. So d by dx mu is differentiation with respect to coordinate. Okay. After computing d mu of VA, I could replace this index mu by a local Lorentz index using an E. But if this is not a covariant object under GCT or LLT, then I can do any operation on it I like with lots of ease and it's not going to become covariant. And what you might guess is that this is not a vector under LLT actually. It's a vector under GCT. GCT blissfully doesn't care because GCT says, look, this is a scalar. You've just taken ordinary derivative of a scalar, so we are fine. So this is no and this is yes. But it's not an LLT vector and let's see why. Well, VA goes to lambda A B B B, then d mu VA goes to d mu lambda A B B B equals d mu of lambda A B. So you see all the problem is because it's local, depends on x, plus lambda A B d mu of BB. Now this is all that we wanted. If this was only term there, then we would have said that it transforms like an LLT vector, but bad news, this is there. Okay. So how do we cure this? By now you should know. Yeah, covariant derivative. There's always, in life, whenever there's such a problem, there's always a covariant derivative. It solves this problem. We just have to find out what it is. But it's not the one we've been talking about all this time, because that was covariant under general coordinate transformations, and now we want to be covariant under LLT. It's totally different thing, and the formula looks totally different. It has some similarities. The first thing, of course, is that we'll just define it, d mu VA, by saying, well, let it be the ordinary derivative plus a linear term. Okay, that's reasonable. So the linear term we'll call omega mu A B B. This structure is perfectly general because it's just a linear transformation on B with all the required indices. But now we have to find the right properties of omega. Yes, yes. Yes. Rotation on the frames. What happens in a general coordinate transformation is coordinate system changes, but the frames also change to the new coordinate system. So these objects, VA, they don't change because the changes compensate between the change in the frames and the change in the tensor. Good. Okay. So now let's find out something about omega. So for that, let's assume the following. Del mu of VAWA. VAWA, so WA is a covariant vector under LLT, but it's nothing but this contravariant vector which has been lowered by eta AB. It's quite trivial. Okay? Anyway, whatever it is, this thing is an LLT scalar. So d mu of it should be d mu VA times WA plus VA d mu WA. Now, we also want this to distribute as capital D mu of VA into WA plus VA capital D mu of WA. This is exactly how things worked when we were doing general coordinate transformations. Given the covariant derivative on contravariant vectors, we could find out what it was on covariant vectors by this kind of requirement. Then take a scalar. On a scalar, there's a unique derivative, so you can call this ordinary or covariant, whatever you like. As an ordinary derivative, it distributes. As a covariant derivative, it's supposed to also distribute. That's the job of the covariant derivative. So require this. Now let's expand this out. First of all, we get d mu va wa from here plus va d mu wa from here. These two terms match those two terms. The extra terms are the omega terms. Omega mu a b v w a, and here we get omega mu a b w b. Okay, so comparing the two sides, we see that this whole thing must add up to 0. It's convenient to think of omega mu having both its indices up. I emphasize that you can always raise and lower them. So this b and this b, we can just raise one and lower the other. Eta does that. So omega mu ab into b w a plus b a w b 0. B and w are completely general, and this is a symmetric tensor made out of them. Therefore, the symmetric part of omega is 0. Therefore, omega is antisymmetric. This is very interesting. First of all, the affine or Christoffel connection that we encountered in general relativity is not like this at all. It has three indices of the same, all general coordinate type, but one upstairs and two below, and then it's symmetric in the two below. This is quite different. It has two indices of different types, two of the LLT and one of GCT, because of the job it has to do. It has to do this job, so it has to be like that. And then it's antisymmetric. Yes.
Actually, they are symmetric. They have this torsion term.
Yeah.
Romantic compatibility.
Yeah, that's correct. And actually here we'll also see that's correct. Here also you could argue that this didn't have to be the case. So it's, yeah, I'm giving you some simplified version which is applicable for us. For physicists, this is quite enough. Okay. Good. Now let's try to compare. Okay, so now let's try to find the transformation law of omega. What is the job of omega? It was to cure the non-invariance of the covariant derivative. So we should evaluate the covariant derivative in two different ways, compare it, and we'll get the transformation law of omega. It comes out very nicely. So let's look at d mu b prime a, where b prime a is an LLT transformation on b. Okay. So first of all, this is equal to d mu b prime a plus omega prime mu a b prime b, where omega prime is the new omega after the LLT transformation. But at the same time, this is also equal, we assume, to lambda ab d mu vb. This is our requirement, that even after differentiating, it should still be an LLT vector. So it should transform like this. Okay. And this is equal to lambda ab into d mu bb plus omega mu bc c. So now you see that we have nothing much to do except collect terms. So this is one side. This side we can look. This thing gives me d mu of lambda. So let's write this d mu lambda a b b plus lambda a b and then this. This is lambda. Alright. So this is 1 and this is 2, and they have to be equal. So some term better drop out. I think this term drops out, this term drops out with that, and we finally end up with omega prime mu a b lambda b c CBC plus this is equal to lambda A B omega mu CBC minus this term brought on the other side. Okay. Now we can drop V because V is an arbitrary vector. As long as we relabel all the indices in such a way that the index of V is common, we can drop it. So let's just rename this V as C. Now we can drop C from this whole equation, VC from this whole equation. So we learn that omega prime mu A B lambda B C is equal to lambda A B omega mu B C minus B mu lambda A C. Now, one nice thing about the Lorentz transformations is that they are also invertible. Okay, so I can write multiply. This is a matrix equation. Actually, as a matrix equation, it's much simpler. Omega prime mu, I'll just put this for AB, and then lambda is a matrix. We see then it's matrix multiplication. This is equal to lambda omega mu minus del mu lambda. Okay. So now I just multiply on the right side by lambda inverse, and I get omega prime mu is equal to minus del mu lambda inverse plus lambda omega mu. And we see that the second term is the homogeneous transformation. Is the transformation that omega would undergo because of having two LLT indices. The one up and the one down, one gets a lambda, one gets a lambda transpose, which is the same as lambda inverse. But this term is new.
Because it's local.
It's
Because lambda is local. That's what it is.
yeah, it's there only because lambda is local. If lambda was constant independent of x, then this term would be 0. Okay, so wonderful. Now the question is, where have you seen a beautiful equation like this before? No, Christoffel symbols don't transform like this. They do transform inhomogeneously, but their transformation equation is nothing so pretty as this one written in terms of matrices, where lambda is a matrix valued in the Lorentz group. Okay, so it's a matrix satisfying lambda, eta lambda transpose equals 1. Okay, so there's a group theoretic meaning to this, which is not present when the Christoffel symbol. In Christoffel symbols, all you ever see is del x prime by del x or del x by del x prime. But the group of general coordinate transformations is a mess. It doesn't have a structure that it's a copy of a well-known group at each point of the space. Here it is the Lorentz group at every point of the space. It's like a gauge group. If anybody here has seen Yang-Mills theory, this is exactly the transformation law. Yang-Mills. This is only for those who have seen it. If you haven't, okay. If you haven't seen it, then when you study Yang-Mills theory, you can say, aha, the Yang-Mills connection transforms exactly like the spin connection, which is what this is called. So, like Yang-Mills connection. So in the Yang-Mills connection, what happens is that we have a matrix A mu, which is like a generalized photon. In fact, it describes things like gluons and W plus and minus and Z bosons in nature. And it transforms under gauge transformations as A mu prime is minus del mu G inverse plus G A mu G inverse, where G is an element of the group relevant to that Yang-Mills theory, which could be SU2 or SU3. So, for example, in QCD it's SU3. Okay, so I think you can see very clearly the similarity, but also the difference, which is that here the group is SO3, 1, the Lorentz group. Here in gauge series, the group is compact, it's SU2 or SU3. It can also be U1. If it's U1, then G and K will commute and this G will cancel that and only this term will be left. That's the familiar gauge transformation of electromagnetic. So it's very beautiful that only after going to orthonormal frames, we see a connection of the formula of general relativity, only one of the formulae so far, with the formula of gauge theory. Everything is a generalized connection on a tangent space, actually on a particular bundle, and omega is called the spin connection. The reason for the word spin is also interesting. The orthogonal groups are sometimes known as spin groups. There is some subtlety which allows us to call them spin groups. So it's a spin connection because it's related to some orthogonal group. It has to be an orthogonal group, remember, because the group arises as the group of norm-preserving transformations of the tangent space. So in ordinary space, it's an orthogonal group, and in OD and in space-time, it's the group OD, 1. That's the only difference. Okay, good. So now probably you can guess what's coming. It's very, very simple, and then we are done. Well, there are two things to be done here. One is, how do we determine W, omega? And the answer is, consider E, A, mu, E, B, mu, theta, A, B equals A, B, mu. And let's act with d lambda on both sides. So we have d lambda on this equals d lambda on that. What's d lambda on this? 0. That's now the usual d lambda. This has no LLT indices, so it's the usual d lambda. But here, what is d lambda? So we have d lambda E mu A, E mu B plus another term is equal to 0. Where the definition is, this is ordinary d lambda of this minus one term because it's got a general coordinate index plus one term because it has an LLT index. This is the covariant derivative of our orthonormal frame. It has two terms, one involving our familiar Christoffel connection and one involving our new spin connection. Because it's a mixed kind of object with one LLT and one GCT index. So there's always a term, one term for every index.
So this capability is kind of, total covariant derivative in the sense?
Yes. And only total covariant derivatives are guaranteed to be give objects which are covariant under both GCT and LLT.
So, if I operate this total covariant derivative on G mu,
yeah, so that is two terms on the left side. Now this times E plus the term on the second thing. That has to be 0. Because on G there is no LLT index, so there are no extra terms for
okay.
No. Okay. Now, it's not necessary, but at our option we can choose to impose d lambda E A mu equals 0 separately on E itself. That means both of these terms vanish separately. This corresponds to a particular choice of spin connection because if you look at this equation and make it vanish, you see that we know everything. This is derivative of E, this is gamma of G, but G is determined as E squared, E transpose. So it's a function of E. The only unknown is omega, and this E is invertible, so we can remove it from here. We can solve this equation for omega. So we learned that omega lambda AB is equal to E something. You can this minus So this is a particular choice of the spin connection, and it has a name. This omega is called the Levi-Civita spin connection. Okay. So I'm not going to write out. You can simplify this and write it in many different ways. But the basic idea is everything on the right is given in terms of the ease alone. So it determines omega as a function of the ease. This is new compared to Yang-Mills theory. In Yang-Mills theory, A mu, the gauge field, is a fundamental field. But in gravity, omega is a derived field in terms of orthonormal frames, and those are the fundamental. Okay. So the last thing, you probably can guess what it's going to be. Let's take a vector VA and calculate d mu in two different ways. d mu on this minus d mu on this, and see what we get. Whatever we get, we know now from covariant derivatives that the answer of such a thing is typically a rotation of this, but the rotation is parameterized by these two indices, so we'll have to call it R mu nu A B on VA or VB. And the computation is very simple because I've already told you how to define D. And notice that after the first D, the second D is no more complicated. It only acts on the LLT index, where this doesn't introduce a new LLT index. Okay? So it's an easy calculation. And what you find is that R mu nu AB is most easily expressed as a matrix R mu nu. So it's a second rank tensor under GCTs and a matrix in AB, which is given as del mu omega matrix nu minus del mu omega matrix mu plus omega matrix mu comma mu comma. This is exactly the same formula as you have in Yang-Mills theory for the field strength F mu nu in terms of the Yang-Mills potential A, and it generalizes Maxwell's relation that F mu nu is del mu A minus del mu. So the last question that you can ask is, well, this is a completely new type of quantity R mu nu. Okay, it has two GCT indices and two LLP indices. What would happen if I used the orthonormal frames to convert these also into GCT indices? I can do whichever way I like. So I can define R lambda rho mu by starting with R mu nu AB and multiplying with E A rho and E lambda B. So, wrong. E B rho E lambda A. Okay, and turns out this is a difficult, somewhat tedious proof, equals nothing but the familiar Riemann curvature, which we got from similar considerations, but at that time we acted with d mu on something which was a GCT vector, not an LLT vector. The nice thing is we've got an even nicer expression for it in LLT language. It's a very beautiful expression and very easy to remember. Much easier to remember than the one in GCT. But anyway, it's the same. Of course, I can't swear it's the same up to a minus sign, but basically it's the same. Okay, so with that we are done, and I'm done. So thank you very much.
So shouldn't there be a minus?
Shouldn't there be a minus sign? Where? Here? Yeah. Thank you. Here is a minus sign. That looks better. Yeah. Okay. Good. So we are done. So now several things remain to be done in this course, but most of them have to be done by you, luckily. So you do need to see me for your project things. Please start from tomorrow. The sooner you see me, the better, and then start working on your projects. Usually to be found in my office on extension 2422. The third homework assignment and last one I had hoped to give you today, but didn't happen, so I'll put it up on the website and send you a SMS. can give that it's up. The second homework I'll correct whenever I do it. And then we come back to the exam and everything after this. Okay, thank you.
So when should we?
Project from tomorrow onwards. Preferably tomorrow itself. The sooner the better.